In this video, we're going to be looking at the very introduction to solutions, what solutions are, as well as looking at electrolytes and what that means in terms of solutions. First, we want to quickly talk about the different parts of a solution. So a solution has two main parts, the solute. So the solute is that part that's being dissolved. Whatever thing is being dissolved, we would call the solute. We also have the solvent. The solvent, this is the part that's doing the dissolving. So usually in most of our solutions, we would be looking at water as the solvent. It doesn't have to be the solvent, but if it doesn't explicitly say that you're using something other than water, then it's pretty safe to assume that you're going to have water being the solvent in that solution. So your solution, this is just the mixture, the homogeneous mixture that happens after the solute is dissolved by that solvent. And when we think about dissolving, what we want to do is we want to think about what's going to happen at the molecular level, what's going to happen at the particle level. And what's happening when you dissolve something is that the solvent particles come in and surround the individual solute particles, breaking them up and surrounding them such that you no longer have solute particles in close proximity to each other. Instead, each solute particle is going to be surrounded by several solvent molecules. Easiest way to think about a solution is to use one that you're very familiar with. When you make lemonade or Kool-Aid, you end up dissolving sugar into water. This ends up being one of the simplest solutions that we can think of. When we think about this making of the lemonade, dissolving the sugar in the water, well, the sugar is the thing that's being dissolved. So the sugar will end up being the solute. The water is the part that's doing the dissolving, so it's going to be the solvent. And then after it's dissolved, that sugar-water mixture we would call the solution. So we can think about it in relatively simple terms and using a solution that we're pretty familiar with. One thing we also want to talk about in this video is the idea of electrolytes. So what are electrolytes? You maybe heard about them in commercials or seen them on the label of your sports drink bottles. So when we talk about electrolyte, what we really mean is the ability to conduct an electric current when dissolved in a solution. When we think about pure water, so when I say pure water, I don't mean from a glacier in Greenland. I'm talking about chemically pure water, where all you have in there is water. Pure water is a terrible electrolyte. It does not conduct an electric current very well at all. However, things that can be dissolved in the water can potentially conduct an electric current. You may have heard the phrase, water and electricity don't mix. That's why when you're messing with plumbing, you're also not messing around with electricity at the same time. Well, it's not that the water and the electricity is the problem. Water is not going to really conduct that current by itself. It's things that are dissolved in the water that allow that solution then to conduct that electric current. So we have three types of solutes based upon their ability to act as an electrolyte. So we have strong, non, and weak electrolytes. So strong electrolytes, non-electrolytes, and weak electrolytes. And we're going to look at each one of these types of electrolytes. First one we want to talk about are strong electrolytes. It kind of means exactly what the name is hinting at. A strong electrolyte is one that's going to really be good at being an electrolyte. These will readily conduct an electric current. And the reason they're able to readily conduct an electric current is that these strong electrolytes produce many, many, many ions. You get a lot of ions in there. Remember, ions are charged particles, so it's going to be the ions that are in that solution that give the ability to conduct that electric current. It's not from the water itself, it's the ions that are dissolved in water. So how can you identify a strong electrolyte? It's pretty easy. When you look at your ionic compounds, if they're able to dissolve in water, they're going to be strong electrolytes, because as they dissolve, what's going to happen is they're going to produce lots of ions as they're dissolving. So if we look at an example, so one example of a strong electrolyte is calcium chloride, CaCl2. Also notice what we haven't seen a lot of necessarily before are kind of, sometimes we also in equations and things we're talking about the state of matter that each thing is in. So little s means that we're dealing with a solid. So calcium chloride, when you place calcium chloride in water, we recognize calcium chloride is an ionic compound. Metal, non-metal, ionic compound. When we put calcium chloride into water, it dissolves. But when it dissolves, it does not dissolve in whole units with the calcium and the chlorides together. Instead, water comes in and is going to surround each and every individual ion. So what you're really going to have are calcium ions. Now we kind of have a new, it's not really a new state of matter, but a simplified way of describing what we have, the AQ. That AQ stands for aqueous, and that just means that is dissolved in water. Calcium ions are going to be dissolved in the water. We have so many water-based solutions, and water is such an important solvent for us that we want to have a quick and easy way of identifying something dissolved in water. That's what the AQ is for. We're also going to produce 2 chloride ions in this that are also dissolved. Now these chloride ions, even though it says 2Cl-, they're not together. They are individually separated. Each chloride ion is going to be separated by water molecules. So we're seeing that we're producing a lot of ions. In fact, if we think about it, every time 1 unit of calcium chloride dissolves, we're going to produce 3 units of ions. Every time we take 1 calcium chloride and are able to dissolve it, we're going to produce 1 calcium ion and 2 chloride ions. So we get 3 units of ions every time 1 unit of calcium chloride dissolves. So if we have 100 units of calcium chloride, we'd make 300 units of ions. So this is how we're able to produce so many ions out of these strong electrolytes. Next type of electrolyte we want to talk about are the non-electrolytes, or not electrolytes. These do not conduct any sort of electric current. These produce no ions. They'll still dissolve, but when they dissolve, they're not going to dissolve in a way that releases any ions. Non-electrolytes are pretty easy to identify. We would recognize these as the covalent or molecular compounds. A good example of this, one we're familiar with, is glucose. Glucose is the sugar that is in our blood. We know it's soluble in water, blood being a mostly water-based solution. So the formula for glucose is C6H12O6, and glucose is actually a solid. Right away you recognize this is a molecular compound, or this is a covalent compound. We don't have any sort of metal, non-metal thing going on in here. There's no polyatomic ions. There's nothing that would indicate we have any sort of ions present. So glucose, as we know, it's dissolved in our blood, and blood is mostly water. Glucose is soluble in water. So when you place glucose in water, it will dissolve, but it dissolves as entire units. There's no ions present, so if there are no ions present, you definitely can't break up into ions. So glucose will still dissolve. Glucose units are still individually, each one is separated from other ones and surrounded by water molecules. But none of them break up into ions because it isn't an ionic compound. If you had 100 units of glucose and you dissolve 100 units, you would get 0 units of ions. If you had 1,000 units of glucose and it dissolves, you would still get 0 units of ions because glucose isn't capable of producing any ions when it dissolves. So the last type of electrolyte we want to talk about are weak electrolytes. And these are kind of the middle ground. We've already seen strong electrolytes produce lots of ions, readily conduct an electric current. Non-electrolytes produce no ions and don't conduct any sort of electric current. Weak electrolytes kind of in between land. The weak electrolytes partially conduct an electric current. And the reason they're able to partially conduct an electric current is they produce few ions. Not nearly as many as ionic compounds do for our strong electrolytes, but they do produce more than the 0 that are produced from the non-electrolytes. So they produce a small amount of ions. Weak electrolytes can be very difficult to identify just based upon their formula. Your strong electrolytes, you should be able to very easily identify you're dealing with a strong electrolyte. Same with the non-electrolyte. You should be able to very easily identify something as a non-electrolyte. Weak electrolytes are difficult to identify. Generally, for a weak electrolyte, you need a hint that you're dealing with a weak electrolyte. So let's kind of go through what a weak electrolyte will look like. One example of a weak electrolyte is HF, and HF is a gas. When you take HF and you dissolve it into water, it will dissolve. That's kind of the first step. But then once it's dissolved, so now I have HF aqueous, once it's dissolved, something else can happen. What can happen this time is that some of these HF particles can then split up into ions, but it's just some of them. How do you know it's just some of them? Well, your kind of hint and your clue is the type of arrow you're looking at. If we look at the type of arrow we're looking at, it's one we haven't really seen much of before. Usually we're looking at arrows just going left to right, reactants going to products, but here we have arrows going in each direction. The arrows going in each direction signify we have an equilibrium process. Not all of the HF is going to go to H plus and F minus, only some of it is. It's like a two-way street. Things are going to go in each direction. Now, it might be tempting to say, well, then maybe it should be 50-50. Half will break up in ions, half won't. Well, that's usually not what happens. Generally, when we look at these weak electrolytes, usually over 95%, sometimes 98, 99, 99.5, generally over 95% stay as whole units. Only about 5%, and often less than 5%, break up into ions. So if we look at something like HF, if we started with 100 units of HF, and let's just say 2% of them break up, so 100 units of HF, if 2% of them break up, well, I'd get 2 H pluses and 2 F minuses. I'd get 4 units of ions for starting with 100 units of HF. So I'm only producing some ions out of this, a couple ions, a few ions. So 100 units of HF, I'm only going to produce about 4 units of ions out of this. And the key to looking at this is this double-headed arrow. Your double-headed arrow is key to identifying these. If you just looked at the formula of HF, you would have no real way of identifying that that was a weak electrolyte. You'd look at it and say, well, maybe it's strong, maybe it's not. The only way you would be able to identify that as a weak electrolyte is if you were told, hey, it's a weak electrolyte. Or if you were told, hey, this will only partially break up into ions. That would let you know that, hey, this is a weak electrolyte. Or by seeing the actual equation of how it breaks up, seeing that double-headed arrow would also allow you to identify this as a weak electrolyte. So you can't identify these just on the formula. You need to have a little bit more information. And often it's a double-headed arrow that's kind of the giveaway that you're probably going to be dealing with a weak electrolyte, because that double-headed arrow is saying, hey, I'm producing some ions, but not a whole lot.